Modern life operates entirely on top of microscopic silicon. From the alarm clock that wakes you up, to the power grid that lights your city, to the targeted missile systems of the military, every modern mechanism is driven by semiconductor technology. To understand the engineering at play, look at a modern smartphone processor like Apple's A17 Pro. Housed on that single piece of silicon are 19 billion microscopic transistors. Each one measures less than 3 nanometers across, roughly 50,000 times thinner than a human hair. This massive global demand has created a semiconductor market currently valued at $257 billion. But looking at top-line revenue hides the true economics of the industry. In this market, generating massive revenue does not automatically equal high profit margins. There is a persistent belief that major tech brands design, build, and package their own advanced chips in-house. That is a myth. No single corporation possesses the capability to execute every step of modern chip creation. Instead, the creation of a microchip is broken down into a highly asymmetric, rigidly segmented global value chain. The process is split into 3 main stages: the initial digital design, the physical fabrication of the silicon, and the final assembly and packaging. Analyzing the financial data across these 3 stages reveals a consistent trend. Profit margins shrink the closer a company gets to the physical handling of the materials. To understand where global capital is actually flowing and who extracts the vast majority of the profit from technological acceleration, we must deconstruct this manufacturing pipeline in reverse, starting from the finished physical product and working backward to the invisible code. We start at the very end of the line, the black plastic casing that protects the final chip. This is the domain of the downstream sector. In industry terms, this stage is known as OSAT, which stands for Outsourced Semiconductor Assembly and Test. The physical reality of this stage involves mechanically cutting the raw silicon wafers into individual die pieces, testing them under various electrical and temperature conditions, and connecting up to 100 kilometers of microscopic copper wiring to interface with external circuit boards. Because of the heavy reliance on traditional industrial machinery and raw materials, the financial returns here are the lowest in the value chain. Operating an OSAT facility typically yields a return on capital employed of around 15 to 20%. This segment commands lower margins precisely because it is the least R&D intensive phase of the entire process. It relies entirely on standard physical labor, testing equipment, and materials like copper and plastic packaging. Because the technological moat is the lowest here, OSAT is the most geographically mobile part of the value chain. It requires capital, but not necessarily advanced physics, making it the primary target for emerging markets like Malaysia and India seeking an initial foothold in the global semiconductor trade. Moving one step upstream, we peel back that plastic packaging to reveal the etched silicon itself. This brings us to the fabrication segment. This space is divided between integrated device manufacturers, or IDMs, like Intel, which attempt to both design and manufacture their own chips, and foundries, which act purely as contract manufacturers for other designers. The barrier to entry in fabrication is purely financial. Breaking ground on a single advanced fab today requires an upfront capital expenditure of $10 to $12 billion before a single usable wafer is ever produced. And spending the capital does not guarantee success. To maintain profitability, a fabrication plant must operate with extreme precision, achieving at least a 99.99% material yield rate. Any higher defect rate destroys the profit margin. The company that has mastered this brutal equation is Taiwan Semiconductor Manufacturing Company, or TSMC. Through decades of compound learning and localized supply chains, TSMC has captured 55% of the global market share in contract fabrication, securing operating margins of nearly 42%. No other entity can reliably produce the highest-end sub-3 nanometer chips at volume. Fabrication is a strict oligopoly. The sheer capital intensity combined with the absolute necessity for yield perfection creates an impenetrable economic wall against any new market entrants. But even TSMC relies on external equipment to physically print those transistors. To etch patterns smaller than 5 nanometers into silicon wafers, you need an extremely specific technology, extreme ultraviolet lithography, EUV. works by shooting a high-powered laser to strike microscopic droplets of molten tin, vaporizing them 50,000 times per second. This generates a specific wavelength of light, which is then bounced off flawless mirrors to expose the silicon. In the entire world, there is exactly one company capable of manufacturing the machines that perform this process, ASML, based in the Netherlands. The moat protecting this monopoly is absolute. A single EUV machine contains over 100,000 individual parts. It represents decades of continuous research and development, and a single unit costs anywhere from $80 million to over $320 million. Because there are zero substitutes for their hardware, ASML holds immense financial leverage over the entire sector, translating to a return on equity hovering near 70%. Whoever controls the equipment that prints the atomic layers controls the ultimate ceiling of global technological progression. Finally, we step entirely outside the physical realm. We dissolve the silicon wafer, leaving only abstract architectural wireframes. This is the fabless segment. Companies operating here, like Nvidia, Apple, and AMD, are known as fabless designers. They spend billions of dollars conceptualizing and designing bleeding-edge chip architectures, but they outsource 100% of the physical manufacturing. To map out billions of transistors, these companies rely entirely on electronic design automation software. This creates yet another indispensable choke point, controlled by a software oligopoly of 3 primary companies, including Cadence and Synopsys. Further upstream is the intellectual property licensing model. Companies like ARM supply the foundational microarchitectures that nearly all modern chips use. They operate a pure-play royalty mechanism, effectively levying a private tax on almost every semiconductor sold globally. This chart maps capital intensity on the horizontal axis against gross profit margins on the vertical axis. When we look at the data, the inverse relationship is striking. Foundries like TSMC sit on the far right. They require extreme capital expenditure and in return yield moderate, steady margins. On the top left, the fabless and IP companies, such as ARM, require almost zero physical manufacturing capital, allowing them to achieve gross margins approaching 96%. The highest economic value in the semiconductor chain is captured not by the manufacturers, but by the software and intellectual property entities that never touch a physical product. But optimizing for corporate profit pools has created extreme national security vulnerabilities. Modern warfare is fought with microchips. An anti-tank system like the Javelin relies on hundreds of individual commercial semiconductors to target and track enemy armor. Without access to these commercial supply chains, a military is forced to rely on unguided legacy munitions. Recognizing this, the United States has begun actively weaponizing the industry's structural choke points. By restricting export licenses for advanced EDA design software and placing bans on ASML hardware, the U.S. can essentially starve geopolitical rivals of advanced computing power. These export controls have severely impacted Chinese tech conglomerates like Huawei, cutting off their access to cutting-edge node designs. In retaliation, the Chinese government has allocated roughly $200 billion in domestic subsidies over a single decade to forcefully accelerate their own in-house fabrication. Because those upstream design and equipment nodes are heavily guarded monopolies, the battle for supply chain security is forcing nations to pour hundreds of billions of dollars into subsidizing the only segments of the pipeline they can realistically rebuild locally. This has triggered a massive global shift toward friendshoring. Western governments are deploying enormous amounts of capital, highlighted by the United States' $52 billion CHIPS Act, to incentivize local production. India's strategic entry point into this space relies on a similar push. The government has committed to over $10 billion in incentives, focusing deliberately on downstream OSAT assembly facilities and legacy 28-nanometer nodes, which run standard appliances and vehicles. Establishing these local facilities sparks a secondary industrial capital expenditure cycle. Beyond the silicon itself, an OSAT plant requires an extensive layer of heavy, unglamorous infrastructure. A single facility requires hyper-specific auxiliary suppliers. It needs contractors capable of building ultra-pure water filtration systems, miles of high-grade stainless steel piping to prevent contamination, and specialized cleanroom heat exchangers. Furthermore, a semiconductor plant consumes huge volumes of specialized industrial gases, like argon and nitrogen. This creates highly lucrative, localized monopolies for the specific companies equipped to build the bulk gas silos and conditioning units required to feed the factories. While the ultimate profit margins remain locked in Western IP and Taiwanese fabrication, the most aggressive rate of localized capital expenditure is quietly shifting to the industrial supply chains of geopolitical allies securing the down.